So what I'm going to do today, I'm going to go through a lot of chapter 5. And I'm going to do the review tomorrow, and I'll post the video online for everybody to see it, and go from there. My concern is that I'm watching the calendar, and it looks like that we're getting kind of tight. We only have next week, and then 3 weeks of November, and then the last week of December is really the final, or the first week of December, last week of the class is finals week. So we got to be careful with that. So I'm going to go through a bunch of chapter 5 today, just to kind of get us going. The homeworks and the quizzes are all assigned, so you can see the due dates for those. And the homework, the due dates for those should be the same as well. So you should be good to go. Everything's set, but I want to make sure I catch up on the lectures and get through that first. Give you some insight on these sections, and then I'll do a review tomorrow and post it online. Now, what we're getting into in chapter 5 are these polynomials, and we looked at adding them and subtracting them. We looked at what they were. There's one thing we want to look at, it's multiplying and dividing them. And the first way we're going to view this is multiply them, and then knowing how the polynomials are multiplied, come up with ways that let us undo that multiplication. So in a way, it's sort of like this. 5 times 3 is 15. We know that to be true. Then, to divide 15 up, we use the fact that we know it's 5 times 3. Now, this might seem kind of silly, but we're going to use this approach when we work with dividing polynomials. So, for example, let's say we're given the number 20. Now, let's say we're going to break it up. And this is sort of a way of dividing it into parts. So since we know 4 times 5 is 20, we can break 20 up into, well, 4 times 5. So if we know how something is put together, we also know how to take it apart. And we're going to use the same approach with polynomials. So let's start off with this. So I'm going to call this greatest common factor. Put some order to this, because this can get a little bit unwieldy. Now, factoring is a way of breaking components into their constituent parts. So when we come up with the factors of 20, we have 4 times 5. So let me mention that. Factoring is breaking something up into parts that are multiplied. So factoring is breaking something up into parts that are multiplied. So again, we have our example. 20 is 4 times 5. These are factors of 20. Or we could say x squared y cubed is x squared times y cubed. Or f of x and g of x. This one maybe a little pedantic, but it's whatever f of x is times g of x. So here we have some objects. We break them down into factors. So when we talk about greatest common factor, we're going to try to break up something that was multiplied together by 2 other things, or was the product, no pun intended. Well, actually, yes, product of 2 things. Now, I'm going to start out with the multiplication first, and then the factoring. So this is a particular type of multiplication called greatest common factor. And where this oftentimes comes in are in 2 places. And one of the popular ones is when a monomial is multiplied to a polynomial. Oftentimes we deal with greatest common factor, or GCF, where we have a monomial and a polynomial. Now let's remember what a monomial is. Monomial has 1 term. Polynomial, many terms, or more than 1. It doesn't have to be all many. I'll put many in quotes. It could just have 2 terms, and that would be a polynomial, but more than 1 term for sure. So let me do an example of what this kind of multiplication looks like. So let's say we have 3x squared and x squared plus 3x plus 2. Now here's our monomial. And this is the polynomial. So the way we do this is we distribute. So that means we're going to take 3x squared, we'll multiply it to every term in those parentheses. And so that'll give us we'll use a dot for multiplication, not to confuse it with x. So each term will be multiplied by a 3x squared. So if we do the multiplications, now remember, especially when we're multiplying polynomials, I want to recall our rules for working with exponents. An x squared times an x squared, that will be x to the 2 plus 2, or x to the 4. 3 times 3 here will be 9. X to the 2 times x, that'll be an exponent of 2 plus that invisible 1. So 2 plus 1 is 3. And then we have 6, and then just the x squared. So that's how we do that kind of multiplication. Now, questions about that? So what I'm going to do is I'm going to show you for these different multiplications and factorings that we're going to do, I'm going to show you the multiplication first. And then we're going to look at how do you undo it? How do you factor or undo this multiplication? Now, this is what we get into the greatest common factor. What we want to do is we want to take 3x to the fourth plus 9x cubed and 6x squared. And each of these terms, we're going to break it up until we have a common factor. Now, a common factor is something that will be in this term, and this term. Now, here's the secret. We already know what that's got to be, because we know what we multiplied. What we know is each of these terms has a 3. Now 9 is 3 times 3. So we're going to pull out, we're going to extract that monomial that we inserted into this multiplication. So if you remember, the monomial had a 3 in it. Now it was 3x squared. But here's the 3. We can factor the 3 out. So what else can we factor out? Well, we have an x squared. There's an x squared hidden in here. X squared times x gives you x cubed. And there's an x squared hidden in here. X squared times x squared gives you x to the fourth. Oh, sorry, getting a little ahead of myself. And so step by step, we can pull out the parts of that monomial from each of these terms. Now, this might seem kind of silly because we know we're going to pull out 3x squared. We will deal with a situation where we don't know what we're going to pull out. We're just going to see what we can pull out. So since we have a 3x squared on each of these terms, we can write this. We can reverse our distribution, take us back to the beginning. Oh, sorry, I need a 3 in here. Don't forget to put a 3 here. I want to leave that out. So we've multiplied a monomial in. And then after we've multiplied it in, we've extracted it out. Now, what often happens with your factoring problems is you're not going to know what went in to begin with. You're just going to have to do an extraction and see what you get. So let's say we have something like this. Well, can we factor this out? Was there some monomial, polynomial multiplied here? Well, one thing we can do is we can look for what's called the greatest common factor. And that's the monomial that could have been multiplied into some polynomial to give us this. So let's take a look at this, 12. Well, this is going to be, let's put it like this, 2 times 2 times 3. And if we take a look at 8, this is 2 times 2 times 2. So what do these have in common? Well, there's at least a pair of 2's multiplied together. So 4, 4. So 4 will be one of the factors. So this is what we've got so far. So those are the numbers. Let's take a look at the x's. Now for the x's, well, it's x times x times x times x. And then this one, x times x times x. So what do these have in common? Well, we have 3 x's multiplied together in each of these. So you have 3 x's here. You have 3 x's here. So that means we have an x cubed and an x cubed. So this will be part of our greatest common factor. So we'll leave an x and a 3. Now this time we're just going to leave a 2. And that's as far as we can go, as far as pulling out a common monomial for each of these terms. So now we reverse the distribution. We say, well, we have this 4x cubed distributed into some kind of polynomial. And this is what we're going to get. That's going to be our answer. To get to our original polynomial, we'll take the 4x cubed, we would distribute it to each of those terms. There are questions about that. So let me do another one. I want to do a couple more examples with these. A multiplication, because we want to be comfortable with multiplying and dividing these as well, or multiplying and breaking them up. So let's say we have this. Take a look here real quick. Pick out a good one. So let's say we're going to multiply these two together. Again, this is the monomial. Here's the polynomial. Now, for all that we knew, these have been multiplied together before, and somebody very carefully extracted this factor from each of these terms, and then reversed the distribution, did this. And now we're just going to put it all together again and mess up what they did. All right, well, here we go. We're going to distribute. So again, we distribute to each term. And there we go. There's our distribution. Now this is what everything would look like just after we extracted this factor from each of these terms. But now we're going to try to combine things. So again, multiply numbers to numbers. And keep in mind, again, don't forget your exponents rule. X to the m times x to the n is x to the n plus n. Same thing if this was y or z or anything like that. So what we're going to get, -4 and 3 is -12. X squared x to the 4th is x to the 6th. Y and y squared, y cubed. Negative and negative is a positive. Then, since these are now made into a positive, we're just left with the 4 and the 7. And that's 28. And then x squared and x is x cubed. Y and y cubed is y to the 4th. And then 6 and -4, -24. Because we're adding here, there's no double negative, so the minus doesn't cancel into a positive, it just stays minus. And then we just have x squared, y. Questions about that? So, you can get something kind of messy like this. What if we had to start with that and then factor something out? Well, let's take a look. Let's see. So what we want to look for is a number or a multiple factor that's common to each of these. And we can see something. So for this is 3 times 5. This we could say is -1 times 3. Looks like 3 is going to be a theme here. So I could list this as 2 times 2 times 3, or I could just say 4 times 3. Because it doesn't look like any 2's are going to come out of here. Now, if I'm not sure about that, it's okay to write that as 2 times 2, just to be careful and see if there are also 2's that could be pulled out as well. But it looks like what we've got is a single 3. So there's a single 3 hidden in each of those numbers. So we'll pull it out. So we pulled out a 3. Now what about the x's? Well, we can think ahead about this. There's an x to the 4th, an x3, and an x to the 4. So it looks like the most we could pull out is an x to the 3. And tell me if you disagree. Because this is x to the 3 times x. This is just x to the 3. It's nothing else. So that kind of puts a limit. We can only pull out at most x to the 3. Because only x to the 3 would be common to all 3 terms. Well, that's something else we can extract. So looks like we're getting pretty close to our common factor, that monomial that got multiplied in here. Let's take a look at the y's. Finally, with the y's. Again, let's look at the smallest power of y. That's y to the 4th. So anything else that's going to be common to the other terms and also common to this, the exponent can at most be 4. So y to the 5th, well, that's y to the 4th times y. Y to the 6th, y to the 4th times y squared. So it looks like it's just going to be y to the 4th that we can extract from each of these terms. So xy squared left behind. 3x cubed y to the 4th times just a y left behind. finally, we just have an x left behind. So now we've done the extraction as far as we can go. We have to extract the same number from all three terms, x to the same power from all three terms, y to the same power from all three terms. And that means we have a common factor that's the same for all three terms. They always have to be the same. That means we can assume there was a distribution that was done, and we can reverse it. This is the monomial we're looking for. And that's going to be our answer. Any questions about that? Oh, did I leave something out here? Oh, I forgot a 5. I left out my 5. Or did I leave out my 5? Let me do another one. I apologize. I think I forgot to carry a 5 and to carry a 4. Let me do that again. I apologize. Let me use a slightly smaller one. Let's do this. What I can do, I can write that one up and send it to you. I think I forgot to carry a 5 and a 4 from one of the steps, and they got lost. So let's do this one. I think if I use a smaller problem on a smaller board, it'll be, I'm hoping it's less likely to forget to carry something. So again, let's take a look for commonalities. And if you're familiar with 18 and familiar with 27, what we know is this. A factor that's common to both 27 and 18 is 9. So we can extract a 9. So now let's move on to x. What do we have for x? Now what's common to both of these terms? Well, this one there's only one x. So that means we can only extract a single x from over here. And so we do that. So now let's take a look at y's. Work with it here. So what can we extract in terms of y's? Well, again, let's look at the lowest power of y. It's y squared. So this term has a y squared, and it's the lowest power of y. We can't go any lower than that. We can't go any higher than that for this term. So that means we've got to look for a y squared over here. And there is. It's y squared times y. So we'll extract y squared. Left over y. Just have 2. So now we pull out 9xy squared. We reverse our distribution. We assume we had one. And that's going to be our final answer. So any questions about that? Yeah, I apologize for that last one. I'll write that one up and send it out to everybody. So we're not quite done with greatest common factor. There's a special part of it, sort of a subsection of it called grouping. So we're still talking about greatest common factor. Now, grouping happens when we have a polynomial times a polynomial. Abbreviate polynomial as poly. Now, what we want to do is talk about how we handle the multiplication in this. And so what we're going to do is we'll take this polynomial and distribute it to each term in this polynomial. So, for example, let me just summarize that in words. We'll distribute the first polynomial to each term in the second polynomial. So let me show you what that looks like. Now we're going to look at how to multiply these types of polynomials later. But let me do some of these multiplications that are involved in grouping. And we'll talk about a special kind of multiplication for binomial times binomial later on. Hopefully we'll have time for it. But what we're going to do is this. For this example, we'll take the first polynomial and distribute it to each term in the second polynomial. Like so. So what that's going to give us times 3x, and then 2x plus 1 times 4. And so that's how we distribute it. Now we're not done yet. The next thing we want to do is take this 3x and this 4 and distribute these into these parentheses. So we're going to do this. So we end up getting a couple rounds of distribution is what happens. 2 rounds to be specific. So if we do that, 3x times 2x, 6x squared. 3x times 1, 3x. 4 times 2x, 8x. 4 times 1 is 4. And now we gather like terms. And that's going to be our answer. So all we do is we take the first polynomial, distribute it to each term, and then we get this. And that's our first round. Then our second round, we'll take this, distribute it to each of these. Same thing with this, distribute this to each of these, and we're going to get this. That's our second round. Third round, combine like terms, and that gives us our answer. Let me do another one, and I'll do it more in that kind of a rounds approach. This one's a little more complicated. Let's say we're multiplying these polynomials together. Well, round one. We're going to take this entire polynomial and distribute it to each term. And that's our first round. Questions about that? So for the second round, we're going to distribute these outside terms into the polynomial that's been passed on to each of them. So we're going to do this. So we also want to be careful with this one. We've got minus signs here. We're going to have to distribute those also. We'll save that for the end. So if we do that distribution, we'll get 7 x to the 4th plus 14x cubed plus 7x squared minus, I'm going to keep my parentheses until I distribute the minus signs. 2 times x squared is 2x squared. This will be 4x. And then 2. And then, oh, I skipped one. Sorry about that. It's be one of those days. Let's do this 8x first. 8x times x squared. 8x cubed. 8x times 2x. 16x squared. 8x times 1. 8x. And then now we distribute the 2. 2x squared plus 4x plus 2. Now we still need to distribute the minus sign. So if we distribute that minus sign to each term in here and here, we'll get this. Minus 8x cubed minus 16x squared minus 8x minus 2x squared minus 4x minus 2. So questions about that? So now we combine like terms. Distribution's all done. Got a 7x to the 4th. I have a 14x cubed. So I'm going to actually cross that out as I go. So we got a 14x cubed, negative x cubed, 8x cubed, and that's it. Those will combine to a 6x cubed. And then we have a x squared, 7x squared, negative 16x squared, negative 2x squared. If we add those up, we're going to get, let's see here, negative 18 plus 7, negative 11 x squared. Negative 8x and negative 4x. Negative 12x. Finally, subtract 2. And that's going to be our answer. So any questions about multiplying these polynomial to polynomial? So let me show you one more thing then, because we've talked about how to multiply polynomial to polynomial. Now we're still in the grouping part. What if we want to undo these multiplications? And this can be kind of tricky, I'll admit. But let's take something like this. So we're going to undo the multiplication. Abbreviate multiplication. Or again, this is what we call factoring. So let's say we're given something like this. Look for one in here. So what we want to do is we want to try to turn this into a product of two polynomials. We want to factor a polynomial out of this one. Now, I'll admit, it seems like a tall task. One thing we can do is this. Let's first break this up into pairs of two terms. We're going to break it up into two groups, and each group has two terms. So let's say we go with this. So those are our two groups. Now we want to be careful of something. We want to make sure that when we group things together, there's something we can factor out. Usually want to be careful of that. But this is what we call factoring by grouping. Now, sometimes we actually don't have to pull something out of both terms. And we can do an example where that's the case. But let's continue on with this one. So we have two groups of two terms. And let's see if we can factor something out. So we're looking for a greatest common factor for this group and a greatest common factor for that group. In fact, let me just put it as plural. Can greatest common factors be found for each group? Well, let's take a look. Well, we've got our first group. We've got our second group. What's common to those two factors? Well, it's not going to be the numbers. 2 and 3 is just 2 and 3. But we do have an x squared and an x cubed. That means there's an x squared here, and there's an x squared times x that gives us x cubed. So we have a GCF of x squared. So what about this one? Well, we have an x and no variable, so we're not going to do anything with variables. But we do have a 2 times 2 and a 2 times, say, -3. So we can pull out a 2 for the GCF. So we factor out the x squared from here. Another pin. Factor out a 2 from here. Now, what we're trying to get at is some polynomial. Since we're going to try to undo polynomial times polynomial, well, when we actually did that kind of multiplication, we took a polynomial and multiplied it to every single term in the second polynomial. So what we're doing to undo this is we want to get some terms that have the same first polynomial multiplied to it. Now we're very close. 3x minus 2, 3x plus 2. What can we do here? Oh, I'm sorry. Oh no, I think that's good. Oh, I made a little mistake. Pardon me real quick. Do one thing, I gotta be careful with my minus sign. Let's see. Let me back up a little bit. A little carried away. For this one here, you gotta be a little careful with this one. The reason is, we can call this negative 2 times 3. And this one, we could call 2 times 2. But the problem is, sorry, I missed my minus sign here. This one's going to be interesting. We don't have anything in common here for this second group. But we could have something in common. Instead of 2 times 2 is 4, negative 2 times negative 2 is 4. We can do that. So the negative 2 is what we're going to pull out. And that'll leave a 3 and a negative 2 behind. So now let's come back to this. We pull out that negative 2, and we're left with a 3, and we still have the x, and a negative 2. There we go. Now we're all right. So any questions about that? I'll do another one of these without the minus signs, because that gets a little confusing. But that's a trick to keep in mind. When you get a situation like this, well, negative 2 times 3, or maybe negative 3 times 2. And this, naturally, we tend to say it's 2 times 2. But if we need to, go with negative 2 times negative 2. That also would give you that positive 4. That might free you up to make sure that the 2 here is negative and not the 3. Then you've got something you can factor out. So now we've got that situation where it looks like we've got a first polynomial that was multiplied to each term of a second polynomial. So reversing that distribution, that's going to be our answer. Now let me do another one without those minus signs, because that can be a little confusing, just so we get comfortable with the idea. Let's see, here's a good one. I think this one will be okay. It shouldn't give us any, we'll have a minus sign, but it's not going to give us any difficult factoring. So again, let's break this down into groups. Now, if we do that, let's say we go with this group, this group. What's the greatest common factor for this? Well, really the only thing in common between these two terms is x. And the only thing in common between these two terms is actually going to be 9. Because 45 is 9 times 5. So if we pull out the greatest common factors, we've got y minus 5 and y minus 5 common to both of these terms. When something's common to all the terms, you can factor that out. That's reversing the distribution. And that's going to be our answer. So let's play with this one a little bit. I just want to show you something. Most of these, I think, in the homeworks, they set them up so you don't have to rearrange the terms to do any kind of factoring or group factoring, or so you don't have any trouble with it, I should say. But let's say we had this rearranged like this. So this is for an alternative arrangement. So in this situation, let's say we group things like this. Well, what's the greatest common factor here? Well, there isn't one. I mean, there's an x and a y and a number. And I mean, this is 3 times 3 times 5, but there's no numbers here. Here's an x and a y, so nothing with variables. This is 5, that's 3 times 3. So this one doesn't really work. So you want to be careful with your arrangement in some of these. Now, the ones they're going to give you in the text and the homework, they're sort of set up where if you group the first two, group the next two, you should be all right. But it is possible to mix things up to where it's really going to be hard to do anything. So just keep that in mind. That could be out there in the future. So let's do another one. This was a little abstract. All right. So again, what I'm going to do, we're going to do this by grouping. Let's group the first two terms. And then these last two terms. Now let's take a look at the last two here. is there anything we can factor out? Nothing. Y's and a number and y's, and that's it. Are we in trouble? Turns out no. That's not always a bad thing. Now what can we factor out over here? Well, there's an x to the n and an x to the n in each term. I don't want to give up on this other side. I want to give it a little bit of help. If you can't find anything that factors out, there is one thing that always does factor out, and that's the number 1. So we can just say 1. So factor out x to the n. And factor out 1. Which really seems kind of silly. But when you get a pair like this, when we're factoring by grouping, we get a pair where we can't factor anything out, it's not a bad idea to say the greatest common factor is 1, especially if it does get a greatest common factor over here. Now let's take a look at this. Turns out a GFC of 1 over here is not going to be the end of the world. Because here is a polynomial that's exactly the same as this polynomial. So we can pull that polynomial out from these two terms. We can extract it. What we'll get and that's going to be our final answer. Questions about that? So you got 3 minutes. I'm going to do one more. Because factoring by grouping can be a little tricky. So a little more practice doesn't hurt. Let's see, let's go with so let's say we got this. Again, and this is fairly safe to do in this textbook. We group the first two terms, then the last two terms. Now, what's the greatest common factor to these two terms? Well, there's nothing we can really do with numbers. But we have an x squared and an x cubed. So we at least have an x squared hidden in each term, or maybe not so hidden. And then for this one, the GFC, well, not much going on with variables. There's a variable and no variable. But 4 is also found in 12, because 4 times 3 is 12. So there's a 4 common to both of those terms. We'll go with 4. So let's extract our greatest, GCF. I do this every semester. I keep calling GCF GFC. That's one of the things you'll just have to bear with me on. We're going to extract our GCF from each of these groups. You get an x squared. I'll leave behind an x for this term and a -3 for that term. And this other one, we extract a 4. We have an x here, a -3 there. And things are looking good. We've got an x -3 and an x -3. So we can extract x -3. that's going to be our answer. If you wanted to get back to the original polynomial, you would take this one, distribute it to each of those terms, and then distribute each of those terms, and then collect all the like terms. And so that's what we're doing with factoring and polynomial multiplication. We can multiply polynomials together, and then if we know how they're multiplied together, we can extract the factors or the polynomials that were multiplied together originally from whatever we were given. So that's going to be sections 5.2 and 5.3. I'll stop for today. Again, I'm going to do a review tomorrow and then post it online. And again, it's just that concern that we're not getting too far behind. We want to make sure we're on schedule to finish. A lot of material coming up. So we've done through 5.3. We have 5.4, and then 5.5 and 5.6. And they all kind of come together, and it's a factoring strategy. And I've got a little chart I can give you on my factoring strategy chart. We'll cross that bridge when we get to it. Other than that, have a wonderful afternoon. If you have any questions, let me know. Office hours start at 2:30, and have a great day. Oh, and for the one real quick, the oh dear, I'll send the message out. I'll send the link out through Blackboard for the review. I'll send out the link through Blackboard. All right, have a great day.